Okay, 1b, methyl lactate is an ester of lactic acid, which is a solvent, used as a solvent. Methyl lactate can be hydrolyzed by refluxing with sodium hydroxide solution. In this reaction, hydroxide ions can act as a nucleophile, suggest how the hydroxide ion acts as a nucleophile. This sort of question, you can be confused by the suggest how there. All right, all it's asking you is what a nucleophile is. So don't be confused by trying. You've only got one line. Don't try and go into detail about how the hydroxide ion is acting as a nucleophile. It's asking you what a nucleophile is. That's just reading between the lines. Okay, a nucleophile is simply defined as an electron pair donor. That's all you need to say. Okay, you can say it donates a pair of electrons or an electron pair donor, as long as you are clearly indicating it's a pair of electrons. If you just say an electron donator or donates electrons, it wouldn't be detailed enough and you would not get the mark. So make sure you refer to the pair there. Next bit, you've got a mechanism. Part of the mechanism of the hydrolysis is shown below. So you'll straight away look at that and go, oh my God, I've never looked at that mechanism before. I've never done that before. I can't do the question. Well, that is utter nonsense. You know how to do mechanisms. You know what these symbols are for mechanisms. You know what mechanisms are all about. This is about applying your knowledge of how mechanisms show a reaction process. Okay? It's asking you then to add curly arrows and dipoles to show how this mechanism would work. Remembering that a curly arrow shows the movement of a pair of electrons, and dipoles are on any polar bonds. So just take it at face value first of all. Look at how it's changing. So the double bond O in step 1 is becoming a single bond O with a negative charge there. The nucleophile, the hydroxide ion, is bonding onto the carbon to give me an OH there. So for this to happen, first of all, electrons must be donating from the nucleophile to the carbon, and for the double bond O to become a single bond with a charge there, that bond must be breaking and the electrons will be going there. So your first arrow will come from the nucleophile, from the negative charge, to be accurate, going onto the carbon, and the second arrow will be from the double bond onto the oxygen. That allows the double bond to break and the negative charge to appear there. Why does this happen? Because the CO bond is polar. Oxygen's more electronegative. It will pull the electrons away. So put your dipole on the C double bond O. So this process would allow this molecule, this intermediate, to form. Now do the same thing again. Look at how the intermediate is changing to become the final product. The double bond O is reforming. So the reverse process of what happened in step 1 must be happening in step 2 to reform the double bond. So let's do that straight away. In that case, the electrons that went there onto the oxygen are going back onto the bond. That's going to allow the double bond to reform. And also then we're breaking off the OCH3. This methoxide ion down here is breaking away. This bond must be broken, so electrons will transfer there from the bond onto the oxygen to allow that bond to break and for this to be removed. And there's your mechanism. There's your 4 marks. It's one mark for this arrow here from the hydroxide to the carbon, the second mark for your dipole and the second arrow there, and 1 mark each, 3 and 4 for those 2 curly arrows. Straightforward. Don't be frightened by mechanisms. And the last question for this section, methyl lactate can also react with ethanol chloride. Complete the equation for this reaction. So ethanol chloride, that's your name for an acyl chloride. Oil chloride is the indicator that it's an acyl chloride, and the ethan is 2 carbons. And you've got the structure here. There's your 2 carbons and your OCl for your acyl chloride. So you're asked to complete the equation. So this is where students can struggle with this, because you look at the molecule here, you see the ester, and you go, hang on a minute, my synthesis maps don't tell me that an ester can react with a carboxylic acid. So the question I can't do, I'll move on and ignore it. Well, look again at this molecule, because you'll be absolutely right in saying that the ester will not react with the acyl chloride, but there's another functional group here. You've got an alcohol, an OH group, on this end, and an alcohol with an acyl chloride will react, and it will produce another ester. So this bit is not going to change, but the OH will form a new ester with the acyl chloride. Now that happens because the chlorine from the acyl chloride is removed, the hydrogen is removed, and that then forms HCl, allowing the carbon to bond onto the oxygen. So this bit of the molecule won't change. Let's start by keeping that the same. So carbon CH3, hydrogen C, double bond O, OCH3. There's going to be no reaction with this half of the molecule, this portion. It's just the OH. Bond coming off to my O. The H will go, the Cl will go, and this bond will form here. Okay, double bond O, CH3, and there's your new ester, and there's your molecule. Now it asks for a complete equation. That would be one of your marks. The second part then is to show the formation of the hydrogen chloride. Okay, and there's the full equation. This is a very good way of making esters. It will produce a very strong yield of ester if you react an alcohol with an acyl chloride rather than the carboxylic acid. However, the production of the HCl means that it's not advisable because HCl is toxic and very, very nasty if you inhale it. So it's not normally done that way, despite the fact it produces a better yield of ester.